did a lot of investigations on this together with my students on Goce and swarm missions in particular. I had CHAMP as well, but I have not included many CHAMP results because they're a bit older. So the contents of my presentation, I will start with an introduction, the satellite missions and orbits that I've worked on and that provide data on the thermosphere and the satellite aerodynamics, the measurement principles and processing algorithms that we apply, and then space weather in the thermosphere. And then there's a big issue that we're currently still working on. It's the uncertainty in satellite aerodynamics and the scale of the thermosphere, of the upper atmosphere. And I'd like to finish with a very special data set that we're going to release early next year, the Goce Reentry Special Dataset. So this is an animation that I made this week. It's a bit dark, but it basically represents the upper pressure level of a thermosphere model. So this is a surface of constant pressure. You cannot really see it very clearly, but this surface, it moves up and down here with the day and the night. You can see it contracting and expanding a little bit. This is a sort of true scale. I try to make it true scale. And then on top of it, you see also temperature. You see a little bit of brighter purple and darker purple. That's the temperature. And this is what the thermosphere looks like when everything is normal and everything is quiet. Of course, when your satellite flies through it, it has a little bit higher drag on the day side and lower on the night side because of this variability. If you have a polar satellite, there's actually a larger effect. If you're over the poles, the Earth is a little bit flattened, so you're a little bit higher up and you have a little bit less drag than if you're over the equator where the Earth is a bit more bulgy. And then this is an animation on a day where something happens on the sun. It's a geomagnetic storm. I will go into more detail later, but you can see that the thermosphere can also be quite violent. So you see these waves that start at high latitudes and then they travel down to lower latitudes. These waves, they take about 3 hours to pass, so this is much faster, of course, than in reality. And of course, when your satellite is flying through such a storm, you will see huge fluctuations of density, and we will see that in the swarm data later on as well. So the satellites that really have revolutionized this type of investigation in the last 20 years, it started with CHAMP. So before CHAMP, we have to go back to the late 70s, early 80s with the Atmosphere Explorer, Dynamic Explorer missions that provided very good data. CHAMP was a satellite, it's called Challenging Microsatellite Payload, to investigate magnetic field and the gravity field of the Earth. It's a German satellite. GRACE was a sort of successor to CHAMP in terms of the gravity field. There were two satellites flying behind each other. And to measure the gravity field, basically there is a problem. You have to measure the acceleration of the gravity field and then the acceleration due to drag and solar radiation pressure. That's basically a sort of nuisance to this type of measurement. So they had very accurate accelerometers on these satellites to measure these, what they call non-gravitational accelerations. And drag is the largest non-gravitational acceleration if you're low enough. So when I started working on this, the Goce mission was already being planned and launched, and I had colleagues in my department working on the gravity and the orbit determination aspects of Goce. Of course, I got the possibility to also use the accelerometers on Goce for this type of work. All of that was also in preparation for an ESA mission, SWARM. So these are 3 identical satellites that are currently still in orbit. All the other satellites that I showed already re-entered. SWARM is probably going to stay in orbit for a very long time, so we can keep on doing this type of research. There's an issue with the accelerometers on SWARM though. They do not work as well as on the earlier satellites. And then there's also GRACE follow-on, which is very similar to GRACE. It's a sort of updated version of the earlier GRACE. Also 2 satellites flying behind each other. The latest that I've heard is that it's going to go into science operations early next year. So if you look at the altitude profile of these missions, you can see that starting in 2000 with CHAMP and GRACE, and then Goce 2009 to 2013, and then SWARM took over. SWARM was launched, I think, 2 weeks after the end of life of Goce. Yeah, we have nearly continuous, or actually a continuous data set, and GRACE follow-on is starting out here. Goce is a very special case because the altitude is so low. It had an ion engine to compensate the drag, and that allowed it to stay at this about 250 kilometer range for a very long time. And towards the end of the life, they took more risk and made it go even lower. You can see here in steps going lower. EPOP, a satellite that's in an elliptical orbit that's been adopted by the ESA SWARM team, but we're currently not doing investigation on the thermosphere. Now, solar activity is also important for drag. The higher the solar activity, the higher the drag. The lower the altitude, the lower the drag. So you have a sort of good signal if you're in this lower right corner. And in this upper left corner, the signal of the drag that you can measure from the accelerations on the satellite, it becomes quite small. And at some point it also becomes smaller than the radiation pressure, or even smaller than the errors that you make in modeling the radiation pressure. So I put a line here. I'm not exactly sure where to put this line. You can move it up or down, or tilt it maybe a little bit. But we definitely see that with Swarm B, a large part of the mission is below this line, that we have some problems getting reliable data from it. And also for Grace A and B, when it was flying at the very deep solar minimum in 2008. And more recently also Swarm A and C, as we're moving into a new, very deep solar minimum. Of course, if you're not interested in the thermosphere, if the thermosphere is a nuisance to you, this very low signal, it's only a good thing, of course. So, but for me, for doing investigations, yeah, I'd like to have a good signal. So the orbital planes, these are all polar orbiting satellites. Goce was in dawn dusk, nearly sun-synchronous orbit. It was not maintained to be sun-synchronous, so you can see a very slight drift over the lifetime. And you see Champ and Grace, but also Swarm has this precession of the orbit that takes a couple of months to cover all local times. Yeah, that's also interesting because, of course, the upper atmosphere is very closely tied to the sun. So you want to make measurements at midnight and noon as well. If we would have only had Goce, we would never had any measurements at midnight and noon, for example. So that's the introduction of the satellites, the measurement principle. So all of these satellites carry accelerometers, and on most of the satellites they work quite well. Accelerometer is basically a proof mass. So this is a block. This is for the Champ satellite. And it's basically a satellite within a satellite. It's supposed to be free floating, just like the satellite is free floating in space. This block, this little piece of metal, is free floating inside this cage, which here consists of 3 parts. And here on the right you can see when all the 3 parts are put together and this little block is inside of it. So this cage has this very peculiar shape because they are basically electrodes. So you can apply voltages to each of these plates. And if you do that in the correct way, this proof mass will be free floating. And of course, the voltages that you have to apply are proportional to the accelerations that the satellite experiences from the outside. So this accelerometer is put in the center of mass of the satellite. So all the gravitational accelerations, they are exactly the same for this mini satellite inside and the big satellite that is surrounding it. But for example, if particles hit the outside walls of the satellite, then you get drag on the big satellite, but of course the proof mass is shielded from drag, so it wants to move relative to the big satellite, and then the electrodes have to keep it in place. So we can then convert these voltages to accelerations, and in the end accelerations to drag. All of the accelerometers have some issues on very long timescales. So they tend to have a sort of bias, drift, and you need to correct for that. And traditionally we do that by also estimating accelerations from GPS. And this works basically the same way as a GPS in your car. We have a little bit more sophisticated GPS receivers on all of these satellites that can receive dual frequencies and record the phase of the GPS signals. And with that we can calculate the orbit to 1 or 2, 3 centimeters. And we can also, of course, then get velocity and acceleration from that data. And in Delft we have found ways to optimize this to get the best possible acceleration information that we then turn into drag. Because if you process for the best orbit accuracy, you do not necessarily get the best accelerations, and vice versa. Okay, so for Swarm, this is basically the only data that we can use for 2 of the 3 Swarm satellites. I already told you that accelerometer is not working very well. This drift that all of these accelerometers show on the time scale of many days. Swarm shows these types of drifts within an orbit. It's basically a very accurate monitor of the temperature inside the satellite. Basically when the temperature fluctuates because it's moving in and out of the sun, the acceleration signal also fluctuates. So there's a sensitivity there that was not intended to be that large. And for Swarm C we can correct it because there are also real thermistors on the satellite. So we can combine the data to correct for it. For the other 2 Swarm satellites, this is not really feasible. But we have optimized this GPS acceleration measurement type. So I've made this animation for Goce to show the different types of accelerations. So Goce is in a dawn-dusk orbit. Of course you have an aerodynamic acceleration, but the ion thrust is designed to compensate for that. Aerodynamic acceleration also includes components that are due to wind. So it does not necessarily align with the main axis of the satellite. The ion thruster is mounted on the satellite, so it always provides a force in the same direction. Let me start it again. And then we also have radiation pressure, which is a relatively small force, especially for Goce if you're flying so low. And in the case of Gauche, it's also always, because of its down-dusk orbit, more or less orthogonal to the aerodynamic acceleration. So you have to model this ion thrust in the case of Gauche. The other satellites do not have this continuous thrust, so there you don't have to do it. But for all satellites, we also have to model the solar radiation pressure, remove it from the acceleration. And then we end up with an observation of the modeled acceleration. And the modeled acceleration depends on the relative velocity of the atmosphere, which is this blue arrow, which we calculate from the orbit, and the Earth rotates underneath the orbit and drags the atmosphere with it. And then of course you have to have an input for the density. So initially you can take a model for that. And then the satellite aerodynamic model itself consists of a geometry model and a gas surface interaction model. So the gas surface interaction model, it basically tells you when a particle from the atmosphere hits the surface of the satellite, how does it leave it? Does it, exchange a lot of energy or only a little bit of energy? Does it reflect in a specular way like a mirror, or is the chance to bounce off in any direction? So there are some assumptions that you have to put into the satellite aerodynamic model. I have one page full of equations, and I will not go into all of those, but I just want to mention that there is this exact theory. We know how to predict satellite drag in the case of diffuse reflection of gas particles on the surface. So here's the drag coefficient, the lift coefficient, and basically what's important is what goes into it. So here we have the wall temperature of the satellite, of course we have the velocity, we have here the temperature of the gas and the molecular mass of the gas. So the composition of the atmosphere and the temperature of the atmosphere are also important. So this is an exact theory, but of course we do not have all these inputs exactly. We do not have a temperature sensor on these satellites. We do not have a sensor that detects whether we're in atomic oxygen or atomic nitrogen or helium. So we have to also make assumptions, and that's why our results have some error. You can apply these equations. It's basically an equation for a single panel, which then generates drag and lift, also depending on this angle. And of course, drag is much larger than lift. So this is different in space compared to lower in the atmosphere, where you can generate considerable lift. But in this free molecular flow regime, lift is always a very small fraction of the drag. And here I have a zoomed in version that looks at what the lift basically looks like. So you could see from the equations that it's quite a complicated set of equations, but it's really an exact theory, and basically from everything, from all the data processing that we did until now, it seems to be quite exact within the limitations of the unknown inputs that we get. There are also simplifications of this theory. For example, if you have a very short object, satellite that's very compact, you can eliminate some of the terms in this equation on the previous page. And then, for example, you get something that looks more like, really like a cosine here that crosses through this 90 degrees here. So this theory really works, is really necessary if you have these very slender satellite shapes. And if you looked at the photos at the beginning, you saw that basically all of these satellites are very slender because the designers wanted to maximize their lifetime and keep drag to a minimum. But some of these satellites have also been flown in different ways. So this is the normal way that, for example, CHAMP was flown with the boom forward in this very slender configuration, like an arrow. But there were a few occasions where they turned the satellite to its side, just to test things, not only for the aerodynamics, but also for the magnetic field measurements. And then you can apply basically these equations and get different variants of the drag coefficient based on various input parameters. And you can see that for a compact shape, there is limited sensitivity to altitude, for example, but there is this parameter of energy accommodation. This is basically how much energy do the gas particles exchange with the surface. And I've put in here two fixed values, and then there's a sort of theory that this behaves in a certain way. I will not explain it, but then you will get a much larger dependency. This part is actually important. You can see that for a compact shape, if you're flying sideways, there's still a sort of limited range. But if you have this very elongated shape, you become very sensitive to all of these differences. The problem is that in the past, when thermosphere models started to be developed, people used basically a simple theory, and that basically said that for all the objects, they could just use something like 2.2 as the drag coefficient. And those measurements were used in the early thermosphere models, Jacquia models, for example. Later on, when mass spectrometer data became available, they had to calibrate the mass spectrometer, and they took the Jacquia model that was based on this 2.2 to calibrate the mass spectrometer data that went into the MSIS model, which is still more or less the state of the art. But as you can see here, there's very little room to go lower than 2.2. But if you apply the theory in different ways, there is a lot of room to get larger drag coefficients than 2.2. So this is already an indication that there might be a bias in the current thermosphere models because of the way the drag on satellites has historically been treated. Okay, so now we have all these ingredients for our aerodynamic model, and we get a modeled acceleration. Of course, we also get observed acceleration. So this is true Gaussian data, acceleration data that we're putting in here. The direction of the relative velocity then gives the crosswind, and then we can basically scale the acceleration. We look at the difference in the scale of the acceleration, the magnitude of the acceleration, to derive the density from it. And I think in this, that's the light yellow arrow here. You can see that it behaves quite, nervously. This orange arrow is based on the model, which behaves very smoothly. So now we can use the difference between these two modeled and observed accelerations to get density out of it and also wind. And you can see the first step that we do is to basically rotate the relative velocity vector. So we add a little green vector here so that our modeled acceleration matches the direction of the observed acceleration. And that's our first output, is this crosswind velocity. So we can basically measure one component of the wind. The wind, of course, is a 3D vector, but using this approach, we have to assume that the in-track wind has some value, either it's 0 or we use some model, and then we can get the cross-track wind out. The reason that we cannot get the in-track wind is that if you have a variation in in-track wind, if you make this arrow a little bit longer, then also the acceleration becomes a little bit longer. But you can also see that the density basically does the same thing. If you get higher density, you get higher acceleration. And the errors in the density model are much larger than basically the error in the relative velocity that's due to the in-track wind. And that is because basically most of this relative velocity is the 7.8 or so kilometers per second of the orbital velocity, and the wind is only maybe a few hundred meters per second on top of that. Presentation, I will stick mostly to the densities. So the equations that I gave, those are for flat panels. Of course, you can build a satellite, model of your satellite by combining multiple flat panels. There's an even better approach, but it's much more labor intensive, is to make such a 3D model of your satellite with a lot of detail, and then use sort of Monte Carlo approach. And that's basically what a student of mine did for these 4 satellites. We are now transitioning also in the official processing of the swarm data to these models. So this is a sort of portrait of the swarm data for the first 2.5 years. On the x-axis is the time. On the y-axis is the angle along the orbit. So basically every single vertical line here is one orbit of data, starting from the ascending node, so going over the equator, going over the North Pole, going over the equator southward on the other side of the Earth, and then going over the South Pole. And what you can see here is that because of the orbit processes, we are moving through this bulge in the thermosphere that is close to the subsolar point. The sun always heats up one side of the thermosphere, and when the orbit is going in a day-night configuration, you get a large bulge. Actually, there's a little bit of delay, so this is more halfway through the afternoon, and then of course this is in the night on the other side of the orbit. You can see here that the density is getting weaker because we started at high solar activity and we're moving to low solar activity. And if you would extend this all the way up to 2018, it will become very dark because we're now going to solar minimum. 2 of the swarm satellites are moving very close to each other. They're 140 kilometers flying side by side when they're going over the equator, and their orbit cross over the pole, and they keep a separation of 10 kilometers in the along track direction so that they don't collide over the pole. So we can look at the GPS-derived accelerations from swarm A and C. You can see that we can look at the difference in the swarm A and the C density, and this is basically 10 to the minus 15, while here we have 10 to the minus 12. So they're basically sampling the same part of the thermosphere. But you can still see that there's some pattern here, that if one satellite is moving a little bit further in the afternoon, it gets a little bit larger density than the other one, and then when it's past the peak of the afternoon density bulge, it will be the other way around, and the other one will be a bit larger. So yeah, this also gives us some confidence in the data. For Gaussian, I made this analysis of how the data compares to models. So this is 1 year of Gaussian data towards the end of its life. That's basically when it was flying much lower even than in the beginning, and when solar activity was quite high. So these are really the best conditions to get the best possible densities from satellites. And I made a comparison with a lot of different models. So those of you who are working with thermosphere models are probably familiar with NOAA-MSIS, Jacquia Bauman, and DTM. That's the French model. So these are 3 empirical models. Then HASDEM is American US Air Force calibrated model, and we got only the output along the gauge trajectory. We do not have access to the model itself, but we have access to the model output along the satellite track. And then GIDM and TI-GCM and UAMP are physics-based models, so these are very computationally intensive models. The movie that I showed at the beginning was made using TI-GCM. You can see that this peak should be somewhere around 1 if there is no bias between the model and the data. And you can see that most of the gauge observations are a little bit lower than 1. The ratios of the gauge observed over model densities are a little bit lower than 1. So gauge returns a little bit lower densities. And for the physics-based models, it's a bit of a mixed bag. Some of them are providing much higher, so much lower, much higher densities, depending on which model you choose. And of course, how narrow this peak is how well the model does. And this HASDEM model here performs the best. JB 2008 and DTM come next, and NOAMSIS, that's the oldest of the 3 empirical models, it's a little bit lower here in the middle. So we can use this data now to evaluate how well the models do, and of course newer models will incorporate this data, and then you cannot do this comparison in a fair way anymore. Okay, I will not go in too much detail in all the applications. We did a lot of very fun stuff, looking at coupling of the lower atmosphere with the upper atmosphere. It was not so fun when the big earthquake happened in Japan, which caused a huge tsunami. But for example, with Gauge, we flew through an acoustic wave and also a gravity wave that was generated by the earthquake and by the tsunami. So we could detect in space how the atmosphere was set in motion at the ground. Those were very spectacular results of Gauge and shows how sensitive these measurements actually are. But I will spend a little bit of time on space weather in the thermosphere. At the beginning, I showed this geomagnetic storm, and I think that is pretty important if you want to design very low flying satellites. So the origin of space weather is, of course, the sun. This is a famous graphic that is used a lot to explain space weather. We have the Earth here and the sun over there, and you can see that from time to time the sun really expels these huge clouds of plasma, and some of the times this plasma comes into the neighborhood of the Earth. The Earth has this protective bubble because of its magnetic field, it's the magnetosphere, but there can be an interaction between the magnetosphere and the solar wind. So that's one mechanism for putting energy from the sun into the upper atmosphere, into the system of the Earth. And that's an important aspect of space weather. So for the upper atmosphere there's also another aspect, and that's just the radiation of the sun. So the sun also, of course, emits light, and we are very much used to the visible light. But the upper atmosphere basically protects us from this extreme ultraviolet and X-ray radiation by absorbing it. And this part of the spectrum, which is very weak compared to the visible part, it contributes also to heating of the thermosphere. So the visible part of the spectrum of the sun is very stable. We do not really see an 11-year cycle when we go out and look at the sun. Visible light, but if you look at the ultraviolet and X-rays, there's a really strong difference between low solar activity and high solar activity, and there's this 11-year cycle that basically controls that. So those are the two mechanisms. If you now go back to this magnetosphere, it's basically protecting us. So why does this matter? So this is a little cartoonish movie that I made. Basically you have this orientation of the magnetic field of the Earth, and the solar wind also carries particles with it that are charged particles, and they carry with it sort of frozen in, they call it frozen in field lines of the sun's magnetic field as this plasma leaves the surface of the sun. A lot of the time this plasma has a northward orientation, and then you can see that it aligns with the orientation of the arrows at the Earth's magnetic field, and in that case the Earth's magnetosphere really acts as a shield. There's not much energy exchange happening. But during some of these really big eruptions there can also be a very strong negative magnetic field. You can see this compass. They're actually magnetometers that are positioned outside of the magnetosphere on the Sun-Earth line in a Lagrange point. When you see the compass needle basically turning south, you get about 1 hour warning time at maximum that something is going to interact with the magnetosphere. And you can see here that the field line from the interplanetary magnetic field now connects with the Earth's magnetic field. And these red dots are basically particles that then can flow into the upper atmosphere. They also can flow outward. I do not show it here, but they can lose some energy when they collide with the upper atmospheric particles, and that causes the aurora and also can cause heating up of the upper atmosphere in the polar regions. But this is not all. You can see that this then also compresses basically the field lines on the night side, and this has even a larger effect. And at some point you could also see a reconnection of the field lines in this region. So this is basically the tail of the magnetosphere, and that's a sort of a reservoir also of charged particles. And when field lines reconnect there can be a burst of energy that then also flows into the Earth's atmosphere from the backside. And that was what was happening there. Maybe I show it one more time. It's a very short movie. So this is the normal configuration. And this is the sort of geomagnetic storm, the configuration that causes the geomagnetic storm. And you can see a lot of extra energy going into the upper atmosphere from the day side and the night side. And that is causing the aurora and the heating up. So that is also the cause of these ripples that you see originate at the poles, and then it's heated up there, and then of course it's like you drop a rock into a pond, the waves have to travel outwards to establish a new equilibrium. This is another animation I made of the same event. Here you can actually see the data from this magnetometer in the Lagrange point. It's pointing northward, and now it's starting to point southward on this morning of the 17th, so you have to wait another day. On the left you see the magnetometer data from the SWARM satellite and the density data from the SWARM satellite. And here a model of the density. You see here the SWARM data, but there are little circles here that have basically the same color as the model, which means that there's a good match between the model and the data. And now this magnetic storm sets off. You can see here it actually was in two phases, so now it's really starting to point southward, and you get a lot of energy that's being put in by these high latitude currents. So you can see here in the magnetometers that when there's a large gradient in the magnetometers, there are large currents, and that means that there's a large energy input. There are vertical currents here. That's the same type of thing that Nikolai was talking about earlier. So this is the main phase of the storm where you have very high density spanning the entire globe. There's actually a minimum of density now at the poles, because all the densities that travel from the poles, both the North Pole and the South Pole, basically piles up at lower latitudes. So sometimes you actually see also when you throw a rock into a pond, you do not only see the waves going upwards, but later you also see it going downwards. A very deep minimum in density in these regions close to the poles. This is a sort of expert version of the same animation where I actually plot also as a sort of timeline in the left these currents, but I think more interesting here is on the right the densities. So yellow are the observations from the SWARM accelerometer in this case that we corrected for all these issues that we had. For this particular case we could do it. And in the background in blue you see the model along the SWARM track, and we both see it sampled as SWARM passes by. That's basically the fixed blue line, but you also see this moving line, which is basically how the atmosphere is bubbling in time even when SWARM is not there. And now we're getting closer to the storm. Well, we actually have to wait one more day. So this is the day for the storm where everything is more or less quiet, but you can still see a lot of these little ripples in the density data. You can see here it's now 0.6 kilogram per cubic meter. And as the storm hits, I think we will go to 5. So that's actually a factor of 10 almost higher densities during one part of the storm. So now we're approaching the storm. So this is the start of the storm. This is the first phase. Actually the storm calmed down a little bit for a few hours. And then early in the afternoon, there was a second phase of the storm. And here we have a peak that goes all the way to 5.5 or something like that, and another peak an orbit later. So you can really see how wild the fluctuations in the density are. And of course the model and the data do not entirely agree, but at least they agree on the order of magnitude of these fluctuations. For some orbits there's a very good agreement, but for others it's not. And you can imagine how dynamic this environment is, that it's very difficult to really get a good prediction. What we also see is that after the storm, the model predicts much higher densities than the data gives. So actually the real thermosphere cools down a little bit faster than what the model can predict. And that's a limitation in the model. So this data is also used to find these limitations and then maybe to fix that in future generations of the model. So this picture of the wind data from Gotje, as we increase the geomagnetic activity, that's this Kp on the bottom. You can see the Kp increase. And then you can see the wind pattern. Basically you get larger winds if you get such a magnetic storm. This is all bint over various storms. And you can also see that the maximum wind, backward wind, basically moves closer to the equator, it moves away from the pole. And you get within this inner region of the pole, you get a really large intensification of the winds as well. Since time is running out, I want to cover uncertainties in aerodynamic modeling. This is going back to these equations. There was a sensitivity to the energy accommodation coefficient. So the way that the particles either adapt to the temperature of the satellite wall. So the particles have much higher temperature, the gas has a much higher temperature, the thermal velocity. The satellite wall has a lower temperature, and when it hits the wall, the question is, does it stick around there a little bit and bounce around and then lose some of that thermal energy before it goes away, or does it act more like a sort of mirror where it goes away with the same energy as it had? And basically this energy accommodation coefficient is meant to take that into account. If it's 1, it basically means that it bounces around a little bit on the microscopic surface and then goes away with a much lower temperature of the wall. If it's 0, it retains all of its own energy. And of course that has an effect on the drag. You can see on the left here that if you lower the energy accommodation, you get higher drag. So if we take this aerodynamic model and we plug in this lower energy accommodation, we actually get lower densities. Higher drag from the model means lower densities. For these panels that have some sort of inclination, you can see that there's also an effect on the lift. That has a big effect on how we calculate the winds. You can imagine that if you have a lift or a sideways force, the more lift you generate by basically turning the knob on this energy accommodation coefficient downwards, the less acceleration can be explained by the wind, and the winds will get lower. And that's basically what you're seeing in this plot, which is as a function of magnetic latitude for different conditions. This is for solstice and equinox, but basically for this explanation it's not so important. We basically see much larger winds from our data, which is the blue and the orange. The orange is behind the blue, those are just 2 different geometry models, compared to the wind model. And the wind model is a climatological model, so it's sort of averaging out all of the wind data that there is. So you would expect that to have a lower magnitude, but still this is something like a factor of 2 or more. And then if we lower the energy accommodation from 1 to 0.6, you can see that we get a much better agreement. So this is already one indication that maybe this energy accommodation should be lowered. Even if you do not trust the model, maybe the model should have predicted double the wind speed or something like that. I think it's also interesting that basically the wind gets more self-consistent. So when there are deviations in the attitude, it's causing different amounts of lift. And if you do not get this lift exactly right, you misinterpret it and you get an error in the wind, and that only expands this envelope of the wind that you see here. So if you tune it to the right value, you can get much better wind data from this processing. So you might say, okay, there's a lower value for the wind, perfect, let's process all of the data with this lower value. But if you look at the density, if we move to a lower value, you can see that in red here you see the density from the current MSIS model, and the 2 colors below that are again for the 2 different geometry models, the densities that we get from the data. We basically move away from the model for the density. So even if we move closer to the model for the winds, by doing the same operation we move away for the density. So somebody is going to be angry at us, I think, depending on what we choose. So we really have to investigate this very thoroughly and defend our investigations. This is, I think, also very interesting. This is for the different satellites. You also would expect, basically, if you have very good geometry models for the different satellites, that you would also get consistency between the different satellite measurements. Of course, you can split it up into various levels of solar activity. So this is its solar minimum, this is its solar maximum, and this is somewhere in between. And you can see that there's the best consistency at solar maximum. Apparently the models, they do not do so well at solar minimum. So let's concentrate on this one. And here also you see that there's a bit better consistency for these lower values of the energy accommodation coefficients. But I would not be able to tell whether 0.5 or 0.7 or 0.8 or 0.85 or something is the best value from this alone. This is a 3D view of the swarm satellites during a special maneuver. These 2 satellites that were flying side by side. This is the telemetry visualized. And you can see that the satellites, they are normally moving that direction. And at some point the operators did this test where they flip the satellites, make the satellites flip around, fly sideways for a period, and then even fly forwards for a period. So this is a very busy plot, which I just made last week for this type of analysis. Basically you can get here again this relative velocity, that's the vector in blue. Then I have here introduced 4 different versions for these 4 different accommodation coefficients for the accelerations. But I think I flipped the labels around here. So I think this darkest one should be 0.4 and the lightest one should be 1.0. So I will correct this when I deliver the slides. I had not been able to recreate this movie in time. But you can see here basically this is the normal configuration. You see here in the blue lines, you see for these 4 different aerodynamic models, on the left and the right, the 2 different satellites, whether or not there's an agreement between the density observations. So let me get back to the start when it was a little bit cleaner. Here, for example, you basically get these 3 different levels or 4 different levels of density, depending on which aerodynamic model parameter you get. There's also a white line here underneath, and that is the model. So most of the time, the data is a little bit lower than the model, but there are some occasions where it's exactly overlapping. And you can also see here that one satellite is having a slightly different density, but also from the accelerations we see that that is the same. Now when we flip to a situation where one of the satellites is flying sideways, we have to use the y-axis of the body fixed frame to get to these densities. And this is where it gets a little bit complicated. Then you have to look at yellow bars on the left and the blue bars on the right, and they have to match up. And here you cannot really distinguish which of the 4 models is better. At some point, one of the satellites flies with its nose in the wind. And at that point, let me see if I can find a good moment in the movie. Yeah, for example, here. So we have for swarm A a much lower sensitivity to this model parameter, and for swarm C a much higher sensitivity. And here you can actually see that if you look at which of the ones matches best, that's probably this 0.81. So it's the second one from the top, both for the yellow and for the blue. This is actually also an indication that 0.8 is maybe a better choice for this particular moment in time. But you can see that things behave quite wildly. So my student has done some statistical analysis, all these different configurations of the 2 attitude angles for the different satellites. And then you would expect them, for the ideal case, that basically the ratio of swarm A over swarm C density is somewhere within a few % of 1. And that happens for most cases. And then there are these special cases where one of the satellites is flying with its nose in the wind, where there's a very large sensitivity or very large difference in sensitivity between swarm A and swarm C. And all of these intersections, they happen at a value somewhere between 0.8 and 0.85. So this is our latest result that also indicates that this energy accommodation coefficient, a good value, a better value might be 0.85. We're currently using 0.93. And I want to show this to end my presentation. Here I'm showing 4 different density models. So the 3 main empirical models, NOAA-MSIS, Jackier-Bauman 2008, and DTM 2013. And this is showing basically a map with, at the subsolar point, this density bulge for these 3 models. And WACM-X is basically a physical model that covers the entire atmosphere. And you can see that it's a much more detailed model. This is the re-entry of Goce. So on the bottom left, we have here the height of Goce during its last 3 weeks when it ran out of fuel. And it's going to basically crash here. And on the bottom right, you see basically for every orbit sort of time series what the density from the model and from the data looks like. And we actually have 2 versions of the data here. First, I'm going to play this out and we concentrate on the difference between the 4 maps. You can actually see the map of the Earth rotating underneath. So we're fixing our map on the subsolar point here at 12 o'clock. As the satellite gets lower, you will all see that especially for WACM-X, the nature of this variation in the map changes. You see basically a diminishing of this subsolar point bulge, also here for NOAA-MSIS, and you will see secondary maximum crop up, and you see it much more clearly here. And you can see for Jackier-Bauman, for example, it does not represent this at all. It's not very accurate for this lower part of the atmosphere. And now we're dropping to below 200 kilometers, 250 kilometers, and that's the end of the mission. A little bit of a zoomed-in view here on this data. We actually have these different colors representing the different models. And then the black dots are the accelerometer-derived data. There's also a gray line behind here where we have just used the GPS. And you can see that they match very closely. These black dots, they have a little bit more of this, what looks like noise. But I'm pretty sure that this is actually true variations of density that are measured along the Goce track. And I think these are waves basically propagating upward from the lower atmosphere. So it's basically weather from the lower atmosphere reaching the higher atmosphere, causing these little wiggles in the density data. So now it gets interesting. We are now at 200 kilometers more or less, slightly below, and part of the accelerometer became saturated at that point. So the instrument was not designed to measure such large accelerations. And you can see it basically drop until the signal basically drops away. But we still have here in gray this GPS-derived accelerations. And we have that until 6 hours before the actual re-entry, when the last full downlink of the GPS data was provided. And that's it. If you look at the scale of the densities, There you can see during this last phase, now the maximum is 0.8, and here it goes all the way up in the last orbits to 150, which is, let me see, what time is this? This is still more than an hour before the actual re-entry, when the satellite was at 124 kilometers. At that point, we still have some confidence in our orbit determination. So we also have wind, and here you also can see the effect of the saturation of the accelerometers. This may be a bit too complicated plot, just to show that we have good agreement between GOCHE data on the left and H2BOM data on the right. So if you want more explanations on what this plot actually means, just talk to me. Where does all this energy go? Because we have drag basically slowing down the orbit getting lower. Of course, the satellite heats up, and this is a picture from the end of mission operations report. So the mission operators, they also had the telemetry of the temperature of the different components of the satellite. And you can see, for example, the battery here, I think it's the blue one. It went from 20 Celsius to 80 Celsius during the last telemetry that they received. And if you go further towards the back of the satellite, there's also an increase in temperature. This ion propulsion electronics unit also saw a rise in the temperature, but it's much more modest. It goes from maybe 13 to 15 degrees. So I think this was a very interesting re-entry experiment, almost re-entry experiment at the end of the GOCHE mission. You can see here that there's continuous data until 6 hours before re-entry, and then there are a few individual passes. I think we should be very grateful that they scheduled these passes. Unfortunately, they could not get continuous data downlink anymore. They used a station on Antarctica, and actually they hired, of course, a couple of passes. They have to pay the station to track and downlink the data from GOCHE. And at some point they had predicted that GOCHE would re-enter in the Indian Ocean, and they said to the station, okay, we don't have to track it anymore. But in the end, GOCHE passed over all of Antarctica and plunged into the Atlantic Ocean near the Falkland Islands. So they could have even maybe tried to listen to GOCHE during this last half hour or so of its life, and maybe got one more data point for this temperature graph. That would have been really nice, but they thought that already died. Okay, so that's the end of my talk. Yeah, the main message that I want to give away, I talked about a lot of different things, but I think the main message is that computing exact aerodynamic forces and torques on satellites, it's not a completely solved problem yet. Of course, that's also addressed in this project. There are strong indications from the analysis of CHAMP, GOCHE and SWARM density and wind data that the energy accommodation should be lower than previously thought. And this has implications for the scale of the thermosphere. So if we apply these right values for the wind, our thermosphere density is going to be lower than indicated by current empirical models. And that means that if you stick to your same drag coefficients for your mission analysis, you're going to have longer lifetimes. Space debris is going to last longer in orbit, things like that. But I have to give one warning that for practical purposes, mission analysis, for example, it is really important to use satellite aerodynamic models and thermosphere models that are consistent with each other. So maybe if you're still using NRLMs for your mission analysis, it's better not to use this very sophisticated aerodynamic model for the elongated shapes. You will get more consistent results if you use the old 2.2 meters. There's somewhere in between that will maybe give you the best result. All of this should be consistent. Currently it's a bit of a mess, but I hope that also the Discoverer project can help. Thanks.